Okay, so it's time for another example, this one dealing with circular motion. So we have a car with a mass of 1,500 kilograms going over a hill at a speed of 20 meters per second. The shape of the hill is approximately circular with a radius of 60 meters as shown in the figure. When the car is at the highest point of the hill, we want to know two things. A, what is the force of gravity acting on the car? And B, what is the normal force of the road on the car at this point? So for A, this one isn't too bad, because if we want to know the force of gravity acting on any object, we know we can always just take the size of the force of gravity equal to mg. So I'm going to have 1,500 kilograms times 9.81 meters per second squared. So I find that the size of the force of gravity is about 14,700 newtons. Next up, we want to find the normal force of the road on the car. Since we're dealing with forces, we're going to want to think about our system and what object we're interested in and draw our dashed line. So we're going to look at the car, because I'm interested in the normal force of the road on the car. So we draw our dashed line around the car, and we draw the forces acting on the car. So I've got the weight pulling straight down on the car, and the normal force perpendicular to the road acting on the car. We're going to write down everything we know. So I know the mass is 1,500 kilograms. I know the speed of the car at the top is 20 meters per second. And I know the radius of the car is 60 meters. I'm going to just rewrite that so it's a little bit easier to see. V. That's a little better. Okay. So we want to look at the normal force. So we know we're going to use Newton's second law. So we've got F net equals ma. If I'm going to use Newton's second law, I better pick a pair of axes. Right? Now normally we might pick the y direction to be upward and the x direction to be to the right. But when we deal with circular motion, we know that the acceleration for an object in circular motion points towards the center of the circle. Right? That's one of the rules. Whenever we have an object in uniform circular motion, the acceleration points towards the center of the circle. Because of that, and because I want to think of the acceleration as positive, I'm going to go ahead and pick the y direction to be towards the center of the circle. Okay? So if I look at the net force in the y direction, that's equal to the mass of the object times the acceleration in the y direction. And I've got two forces. I've got the weight, so I want its y piece plus the y piece of the normal force equal to may. Move this down a little bit. Okay. All right, the size of the weight is always equal to mg when we're on the Earth. The normal force is pointed up, so that's in the negative y direction for this question. Equals may. Now from class or the reading or the book, right, we remember that the size of the acceleration when we're dealing with circular motion is equal to v squared over r. So that's what we're going to use for the size of the acceleration. Remember, that's one of the neat things about circular motion is we actually have an equation for the acceleration. So the acceleration in the y direction is v squared over r, pointed towards the center of the circle, which is why it has an overall plus sign, because I said that the y direction was positive if I go towards the center of the circle. So now I can solve for the normal force. So the normal force is equal to mg minus mv squared over r. If we plug in numbers, we're going to have the 1,500 kilograms times 9.81 meters per second squared minus the 1,500 kilograms times 20 meters per second, and that gets squared, divided by 60 meters, and that's equal to 4,715 newtons. Okay, so that's the answer, and now we can see if it makes sense, right? So if I just draw it again here, let's go ahead and scroll this down a little bit. Right, so I've got my car going over the top of the hill, and the car is moving in circular motion, so it's going through a path that looks kind of like that. Again, because it's in circular motion, we know the acceleration points down. Since the acceleration points down because that's towards the center of the circle, that means that the net force points down. Since I only have two forces acting on the car, right? I've got the weight pulling down and the normal force going up. I know that the weight has to be larger than the normal force because the total force points down, right? And that's indeed what we found, because if we go up a little bit, right, we found that the force of gravity was about 14,000 newtons, which is certainly larger than the 4,000 or the 4,700 newtons that we found for the normal force. So our answer is consistent with our picture. We know the acceleration is downward because it's towards the center of the circle. So the net force has to be down. Since these are the forces, we got the normal force up, the force of gravity down. We know the force of gravity has to be larger than the normal force, which is what we found. So that's it for this example. Hopefully that was helpful.